So now that we've talked about parallel streams and kind of compared and contrasted it with structured concurrency, let's take a look at yet another concurrency model that came out with Java 8, and of course is still in use today. And this is called completable futures. And we're going to talk about the completable futures framework. Once again, we're going to use it to download images from remote servers, so the tasks here will be largely I/O bound. And this approach is also described in the ex4 project in my Loom folder in my live lessons GitHub repository. So we're back in the ex4 folder and in my Loom project. And this time we're going to take a look at the completable futures implementation for downloading images from remote web servers. This particular approach looks quite a bit at first glance like the parallel streams version we looked at, and that's because it also uses streams to kind of provide the overall control flow. But when we take a look at the behaviors that are run within each of the stream operations, you'll see that they work quite differently. So what this is going to do is, once again, we're going to start by getting a list of URLs, just like we did before. Then we're going to turn it into a stream, almost like what we did before. The difference being that before, in the previous example, we used a parallel stream, but now we're just going to use a sequential stream. And you'll see why we're using a sequential stream, because we're going to get concurrency through other means. So let's take a look at those other means. So another thing to note, just at a high level, notice how we have something similar to before. We have some map operations, and those are going to go ahead and call these method references, which are called behaviors, to do some processing asynchronously. And you'll notice that there's a flat map operation here, whereas before we didn't use flat map because of limitations with flat map for parallel streams, but flat map works perfectly fine in the way we're using it here. And then you'll also notice something else here. We didn't have collect before. We used just toList, but we're going to have collect. But collect's going to do something really cool using a special collector that we wrote called a futures collector. And so I'll show you how that works. So let's go ahead and take a look and see what happens. So for each image that we've been given in our list of images, we have a stream now. And we go ahead and call this method called download image async. And I put async in there for a reason, as you'll see here in a second. You can see what it does is it takes the URL that's passed in as a parameter, and it downloads it just like we did before, and it downloads it in the context of the blocking task call in managed block method, just like we did before. So that'll expand the size of the common fork join pool as needed. But what we do now is we go ahead and we create a new, or we actually go ahead and create a supplier, which is what this thing is, and we tell that supplier, we put that supplier on a queue of operations to be run asynchronously in the common fork join pool. And to do that, we use a factory method called supply async. And supply async is a factory method on the completable future class. And what it does is it goes ahead and takes that supplier and then queues it. Let's see if we decompile the code. This is kind of cool. You can decompile the Java code and see what it looks like. So here you can see supply async takes the supplier, and it calls a method called apply supply stage, or sorry, async supply stage, passing in the supplier and something called an async pool. And if we look at async pool, you can see that async pool is going to most usually be the common fork join pool. And async supply stage goes ahead and makes a new object called a completable future that is not going to be given anything to do. And then we take that new completable future and we go ahead and take the supplier that was passed in and the executor, which in this case is most likely to be the common fork join pool, and we say, hey, common fork join pool, please execute this new async operation called async supply, passing in this supplier that was passed to us. And what new async supply does is it's just a little carrier class that extends fork join task. Keep in mind that a virtual thread also is some extension of fork join task. So this is going to be a lightweight concurrency mechanism. And the bottom line is, without getting too wrapped up in the details, there's a run hook method here. And when the thread pool is ready to run, or sorry, there's an exec method which calls run, and then run turns around and basically will go ahead and call the supplier to get the work done. So here we go. We say, go ahead and get the contents that we're doing, which in this case will download the file, and then store that result into the completable future, and then we wrap up. That's a very, very high-level tour through what goes on in completable futures. So basically, they're essentially queuing up asynchronous events which run in the background when it's their turn to run and do stuff. And in our case, what they're doing is downloading the image. Now, what supply async does is it doesn't block. It puts that onto the queue and then just returns, and it returns something called a completable future. And a completable future is essentially a proxy that can be triggered when the asynchronous computation finishes running. So that's what a completable future is. It's a proxy. And so what we get out of this thing, and it's a little hard to see, but I'll move the screen over just a tad. You can see that we have a stream of completable futures to images. So what that means is that process is taking place in the background and it's not done yet, but we're just going to return a completable future. A completable future is a little bit like a promise or a future in JavaScript. And it's a little bit like a future that we've talked about with structured concurrency in Java, although it's a lot cooler than the Java structured concurrency futures are. So the next thing we do is we call flat map, and you'll see why we're going to call flat map in a second. And we pass in the apply transforms method. And what apply transforms takes in is a completable future to an image. So it's that image that's in the process of being downloaded in the background in the common fork join pool initiated by the supply async call on the completable future. And so what we're going to do now, and this is reminiscent of what we did with parallel streams, but it's a little different. We're going to get that list of transforms just like we had before. These are the things like grayscale, tint, sepia, emboss, whatever. And then we're going to go ahead and create a stream of transforms, and then we're going to apply map. And for each transform, we say, when the image finishes downloading, so we have an image future. So when the image is finished downloading, call this completion stage method, which will then asynchronously queue up this operation in the common fork join pool and return a completable future to that. So the analogy I like to use for asynchronous processing is juggling. So the idea with juggling is you try to keep as many balls in the air as possible and only grab them long enough to switch hands, or if you have one hand juggling, to throw them back up in the air again. So that's the concept of juggling. And the idea here is we want to keep as many things running asynchronously as possible and only do stuff synchronously long enough to make sure we know what we're doing and then initiate another asynchronous operation. Yes? Yeah, so the question was, where's the blocking? So the only blocking that's, and it's not even blocking, it's just computation that takes place in sort of, without running, this is also could potentially running in a background thread, but let's assume it's running in the foreground thread. It's running in the foreground thread just long enough to put things in the background threads to keep running in parallel. So yeah, that's right. So apply transforms is called, and it doesn't really block, but it does some stuff, and what it does is it arranges to run the next round of behaviors or actions, as they call them, in the background. And in fact, if we take a look at then apply async, because we can decompile that code too, you can see that it calls this helper method called uni apply stage, because it's a completion stage method, passing in the default executor and the supplier function that we've given it. And if we keep popping down, we'll eventually see that this stuff is going to get run on the executor, very much like supply async had done, but it's going to run it and it's going to return a completable future to whatever that thing gives back. So in this case, transform will basically transform the image, make a new image, and we'll get back a completable future, as you can see here. We get back a stream of completable futures to images that are being transformed. So that's the way to read that. And the stream, because we don't have a terminal operation, this call returns a stream. So we have a stream of completable futures to images. And that's why we used flat map here. Because what's happening, let's say again we have 30 images. So we have 30 images, we call map on 30 images. We end up with 30 images, a stream of 30 completable futures to images that are in the process of downloading. Then we call apply transforms. Let's say there are 3 transforms. So now we have 90 images being transformed. And flat map ensures that this comes back as a stream of completable futures as opposed to a stream of completable futures. If we used map, we'd have a stream of stream, but flat map works perfectly well in this case. And so we're able to get a stream of completable futures to images that are being transformed. And then the next step is to map, again, using store image async. And store image async, as the name implies, is simply going to do the following. It says, when the image transformation is done, then call this completion stage method called then apply async and arrange to run the storing operation in the background by putting that into the common fork joint pool. So that's what then apply async will do. It'll go ahead and put this supplier in the background and it'll run it. And when that's done, that'll return a completable future to a file, which when completed will have the final result. So how do we terminate all this stuff? So at this point, if you think about what's happening, all these things are running asynchronously, doing downloads. All these things are running asynchronously, doing transforms. And as those things complete, all this stuff is running asynchronously, doing file storing operations. So we've got, at this point, a stream of completable futures to files, but lots of other stuff can be going on asynchronously at this point. So how are we going to get everything put back together so we have one result? Well, the answer is we're going to use the collect mechanism of streams, and we're going to use our custom collector called futures collector. So here is futures collector, and you can see that the toFuture method is just a factory method on future collector that makes a new future collector. Here is what a futures collector is. So a futures collector is our custom class that implements collector, which is an interface defined in modern Java, and we tell it, take a stream of completable futures to objects of type T, whatever they might be, and store them internally in a list of completable futures to objects of type T as they're being accumulated. And then after we process everything to finish stuff up, return a single completable future to a list of objects of type T. So to think about this at a high level, we've got a stream of completable futures, in our case to files. We're going to store them temporarily in this list of completable futures. And then we're going to do some magic to collect all the results together and return a single completable future to the results of the final list of all the processing. So let's take a look and see how this works. So there's a set of overrides that are defined on collector that we're going to implement. And one of them is this one, which is the one that does the supplier. Supplier basically says, it's a factory method that says, tell me what kind of object is going to be used as the mutable result container, what we're going to stick the results of the stream into. And we're going to put it into an array list. And then there's another factory method called accumulator. And the accumulator is going to tell what kind of method reference, or in this case by consumer, to use to add the next item in the stream into the mutable result container that we're accumulating. And we just basically add it. So we put the next item at the end of the list. We have another method called combiner, which I'm going to ignore here because we're not using parallel streams. And then this is the really cool method. This is the finisher method. And this gets called after all the elements in the stream have been accumulated into the mutable result container internally to the collector. And what this does is it says, take that list of completable futures to items of type T, and we can convince ourselves that that's actually what's going on here by expanding this like that. So it's a list of completable futures, which is the mutable result container. And then we're going to use a really, really interesting method in completable future called all of. And all of is essentially a method that will be used to take the list of pending completable futures, the ones that are still off doing their thing, and it's going to make a little array of that. And so it's going to pass in an array of completable futures that are still pending to this all of method. And all of is going to return a single completable future that will trigger only when either an error occurs, an exception is thrown, or when all the completable futures in that array finish. So it's a little bit like the shutdown on failure model of structured task scope. It's kind of along those lines. Not quite, but it's along those lines. So we get back a single completable future that, when triggered, says everything's done. All that asynchronous computation is finished. And then we're going to chain that together with a completion stage method called thenApply. And this method will get called back when that completable future triggers. And what we do is we take the list of futures, which was passed in up here, and this is the list of completable futures that were accumulated during the earlier stages of this. We turn that list into a stream, and then we go ahead and use the map operation to join together each completable future to get the object that has been completed. So completable future join is a method that converts a completable future to T to an object of type T. It's kind of like result now was for future that we looked at in the context of structured concurrency in Java. This call will never block because we wouldn't have gotten this far unless everything had finished. And then the last thing we do is we convert that stream of objects of type T to a list of objects to type T. And what gets returned from this thing is a completable future to a list of objects of type T. And then if we pop back up a few levels, you can see what we end up with here is a completable future to a list of files. And then we call the join operation. This time it really will block because everything may not be done yet. But when it is all done, join will return, and we will end up with a list of files. So we've peeled away all the completable future gobbledygook and ended up with a list of files, and then we go ahead and print how many files were downloaded. So if you recall, when I started this example, I ran the program, and you can see, just for fun, this is interesting, this just shows the inherent non-determinism of parallel processing and networking and so on. This time, completable futures finished the fastest. Remember last time that structured concurrency finished the fastest. But this time, completable futures were faster. But we're talking about a half second faster. So to really get a better sense of what things perform better, we would have to do a more controlled experiment, most likely by removing the network from the whole equation and just working on processing images that are stored locally, maybe in a file or in memory or something like that. So this just gives you sort of a rough order of magnitude. But I wanted you to see that each time you run these things, you may get slightly different results because not everything is fully deterministic when you start working with computers and networks.